Hello, today I would like to demonstrate to you an exciting new feature in ADF 2017, Ligand Field DFT, combining features of ligand field theory with density functional theory, essentially doing a configuration interaction inside the active space of the partially filled orbitals. As such, it allows you to deal with um, particularly difficult configuration, partially filled F and D orbitals. And one nice application of that is for phosphorescence converted white LEDs. And so I'll explain a little bit how that works. In a traditional light emitting diode, you inject electrons into the conduction band and they can relax by recombination with holes in the valence band by emitting a photon. That works for direct bandgap materials, and the wider the bandgap is, the higher the frequency, so you can make blue emitting, red emitting, and green emitting materials. Combine those together, you get a white light. However, if you have a material that itself emits blue light, but is doped with a lanthanide that can emit red and green photons, one can make a device where you emit white light from a single material. And so, for instance, you have a host material such as gallium nitride, which you dope with a lanthanide, and that lanthanide can absorb some of the blue photons emitted, cut them in a process known as quantum cutting, and then emit lower lying or emit lower frequency photons that then give rise to the red and the green color. And so you can get a very nice single white spectrum out of one material. So it will be very nice to tailor the properties of these lanthanides and how they interact with the host materials. And one fairly innovative way of dealing with that and being able to describe excitation processes and thereby de-excitation processes is this Ligand Field DFT method. And so there are two papers that describe particularly this application for white LEDs. And so one is from 2013, which is this particular host material doped with praseodymium ions, and one later paper, which is the one which I will essentially base this demonstration on, from 2015, doping lithium yttrium fluoride with praseodymium ions again. And so hopefully we'll be able to describe these transitions. So F1D1 to F2 transitions. And I will start with a naked ion and then show you a little bit what has been done in this paper from 2015. So just summarizing what LF-DFT does. Again, it's a sort of configuration interaction dealing with the degeneracy that you typically find in open shell F systems and also in open shell D systems, especially the 3D transition metals. And in order to do that calculation, one needs to be able to deal with spin-orbit coupling, which can be done quite efficiently in ADF with the Zora Hamiltonian, and also be able to equally distribute electrons over this open shell in a so-called average of configuration calculation. And ADF happily deals with fractional occupation, so those two requirements are met and therefore can be a good starting point for running the Ligand Field DFT. And in 2017 we managed to also include, with the help of our academic partners, to include the Slater-Condon parameter that one needs for this Ligand Field DFT calculation. So that deals with how specific orbital configurations are split in different terms, and also including some of the algorithms that involve calculating the different quantum states for particular electron configuration and the transition between two different configurations, which also gives you the oscillator strength and thereby the electronic spectrum. Okay, so this is the paper essentially, as I mentioned, that we want to look at. And I'll first demonstrate how one calculates ligand field DFT for F2 to F1 D1 in a naked praseodymium 3 plus ion, and then give you hints on how it was done in this particular paper by putting that praseodymium ion inside part of a cage and then calculating the optical properties of that. So essentially reproducing this particular spectrum here. So we open up the graphical interface and we make a new input, and in the drawing case we put a praseodymium atom. It's over there, and we set the relativity to scalar since this spin orbit is going to be dealt with inside LF-DFT. Choose basis set triple zeta without a frozen core. Increase the numerical quality a little bit, and then finally it's crucial that we set symmetry to no sim, since Ligand Field DFT needs to be used in no sim. And now we need to define which orbitals are going to be partially occupied. So the 7 orbitals over which we are going to smear the 2 F electrons of praseodymium 3 plus. And there are 2 ways that one can do that. If you already know which orbitals are going to be occupied in the details user input, you can set here the occupations key block. If you have a small system such as an atom, you can actually run an ADF guess, which will do a small crude calculation on your system, which will give you an orbital level diagram. It doesn't give you much information as running a single point calculation would, and so you don't see here actually what is the main contribution from the atomic orbitals. So I happen to know that this is a 6s orbital, and sorry, let me scroll a little bit, zoom out a little bit. And as soon as we depopulate that, as will be the case for 3 plus, that orbital will actually go up higher in energy, but that means that these f orbitals and d orbitals, which are degenerate, will become lower in energy, and those are the ones that we want to populate. So these 3 electrons are going to be removed, and those are going to be occupied in the 3 plus ions with 2/7 of an electron. And let me look up quickly what that number is from another run file. So that's 2/7 of an electron. Put that in there, 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 and there. All right, so now if we run this calculation as a single point, we will do this average of configuration where we occupy the first 27 orbitals for no symmetry calculation with 2 electrons, and then the next 7 orbitals, which are going to be degenerate for this system, will be occupied by 2/7 of an electron. And since we know that this is going to be the correct configuration, I'm pretty confident that we can go straight to Ligand Field DFT calculation. And here, after the SCF has converged, we will do the Ligand Field DFT calculation immediately. Here we need to put the MO indices of the partially occupied orbitals. So that was 28 through 34. We want to include spin-orbit coupling, obviously, since it's a heavy element. The main quantum number of this particular shell, it's a 4F shell, so main quantum number n is 4, and the angular quantum number is 3. And then we're good to go. So we save this as praseodymium F2 ligand field, and it will give you a warning. Yes, we know we have fractional occupation numbers, which is kind of an advanced feature. That's why you get a warning, but it's exactly what we need for Ligand Field DFT. So we say OK, and then we run this calculation. And it should take a couple of cycles to converge. So first it will do the atomic calculation and then use the atom for the actual calculation, which is a 3+ version of that, with the electrons also equally smeared over the partially occupied orbitals. Okay, so that's already done, and we can have a look at the orbital level diagram now. And so you can see that this is the neutral, this is the 3+. Obviously the electron levels are shifted down, and we can see if you hover with your mouse on the right spot, which sometimes is a bit tricky, you can see that now we have all these orbitals are partially being occupied with these F electrons, and you can see that further in the output as well. Where if we scroll down to the occupations, so list of all molecular orbitals ordered by energy, there you can see that this is populated by 2/7 of an electron. It's purely F orbitals. Obviously, because it's an ion, it cannot have any involvement from other elements, but as I'll show momentarily, that's not the case when you put it inside a chemical environment. Okay, so it actually ran LF-DFT calculations, so now you get all the energies of the different states with their particular spin orbit coupled quantum numbers, and you can visualize that spectrum as well. So if we go to SEM spectra, you will get the energy of those states in a graph. Okay, so once we've done the F2 calculation, now we want to calculate the other state, which has 1 electron in the F shell and 1 electron in the D shell. Then we want to equally populate the D electron over that particular shell. So we go again to spin and occupation. And now, since we already have done a calculation, it will give you the ADF level diagram of the proper calculation. So we can see that these are in fact the d orbitals. So those are the ones which will populate with 1/5 of an electron. And let me take another run file to get 1/7 of an electron, which is what will be the population of the F shell. Right, so there's 1 electron over 7 F orbitals. So we change all those orbitals to 0.14. So those are the F orbitals, and then 5 orbitals will have 0.2 of an electron, which amounts to 1 d electron. All right, there we go. And now we can run in Ligand Field DFT an excitation calculation. So we input here 35, 36, 37, 38, 39, which are the 5d orbitals. Again, we want to include spin orbit coupling, main quantum number, since it's 5d is 5, and d means angular quantum momentum, orbital angular momentum, L equals 2. And we want to take the excitations from F2. So we pick that tape 21 file, and we save this as D1 F1 F1 LF-DFT. praseodymium. Again, we get the same warning about the fractional occupation numbers. We run it anyway. So there we go. Job, run. And now it will first run the average of configuration for the D1F1 configuration. And then it will compare the excitations from the F2 Ligand Field DFT to the F1D1 Ligand Field DFT. And that should finish in a couple of cycles, hopefully. All right. Now I've picked an atom because that's easy to converge and it's quick to calculate, but I'll give you some hints on how to do it for bigger systems. Let's visualize the spectrum, and by default it will give you just the energies as it did before, but in spectra Ligand Field DFT you can switch to Ligand Field excitations, and here we go. This is the excitation spectrum. In order to compare that to the spectrum from the paper, we switch to 1/centimeters, and you see that these excitations for the naked eye are much higher, and as soon as we embed it in a chemical environment, you'll see that that will lower the excitation energy. But already you can see a similar structure emerge as for the spectrum out of the paper. Okay, so that's how to set up these type of calculations, and as promised, now we'll go to demo a little bit how you would go about to run the type of calculations that have been run in this 2015 paper. So what I've done is, and I'll make a new input, start from the host material, lithium yttrium fluorite, and we are going to import that particular CIF file, which is freely downloadable. There we go. And that will take you from ADF to band. We're not going to run band calculations, but we are just going to use it as a starting point to make a cluster. And we then tell band to make a supercell. Let's say we make a 6 by 6 by 3 supercell. That should be large enough. And then we switch from band to ADF, and then we have a very large cluster. And in that cluster, we zoom in to find a central yttrium. So the praseodymium is going to occupy an yttrium site. So we are going to just select a central one, and then we select within radius, maybe everything within 5 angstrom. And then we invert that selection. So select invert selection, and we delete those atoms. There we go, delete atoms which are not inside the 5 angstrom of the central yttrium. Okay, so this is now used as a starting point. In the paper, you will find it uses a slightly smaller cluster than this, so some of these fluoride atoms are removed. And then you will get a cluster which has 24 fluoride anions, and it has a net charge of -1, and that's used to optimize the distance between the central praseodymium atom and the fluorides, but they keep the outside fixed. So you could change this to praseodymium, and then you could choose everything, yeah, let's say within 3 angstrom. So, and then we'd make that as one region. Okay, so And then again, we make use of this invert selection, and we make a region out of that as well, which is the shell. Right, so we have nice two regions, which will be helpful for the geometry convergence. So you need to delete 8 fluoride atoms, and now I'm just randomly doing that, so I'm probably doing it wrong. I will provide the outputs, the input structure that was used actually for running this geometry optimization. So I still have too many fluorides here. So you'd have to make a judicious choice rather than just randomly deleting some of these fluorides. You want to keep some sort of chemical and also electric environment around all of these ions. But let's say you have a system like that, and again, have the input available. Then one can run a geometry optimization, and in the geometry optimization, that's done with LEA because that turns out to give the best results for the host material itself. We use no core, we use a good numerical quality. Then in the geometry optimization itself, we want to switch to Cartesian coordinates because that allows us to freeze atoms in their particular x, y, z coordinates, and we can add constraints. So we want to, for instance, freeze all the bonds in the shell, and if we go back to regions, we can also select all the atoms in the shell, and then if we go back to constraints, let's do that again, model regions, we select all the atoms in the shell, and then in constraints we say we want to fix all these atoms. Okay, so now, and of course switch off symmetry, which is what we need in the end. It turns out that you need to run also this calculation using average of configuration because it's an open shell system which has these unpaired F electrons, and so you'll find that you will need something like this. So this is the occupation block that you can then put into your user input here. And then you can run this geometry optimization. So save that and geo praseodymium in host. You get the warning, that's fine. And then if you run that calculation, that will do a geometry optimization. As I mentioned, Harry was so kind to send me the geometry that was actually used for this paper, and I've run a geometry optimization with that. So I just kill off this guy here, kill it, okay, and then just show you how that geometry optimization ran. And you can see, as is also described in the paper, that the distance between the praseodymium and the fluorine is increased. So you see the outer shell is kept still, and praseodymium is slightly larger than yttrium, so therefore it pushes out the fluoride atoms. And then in the next step, what's done, you take that optimized geometry, but you only take the central part of that, the praseodymium with the 8 surrounding fluoride ions, and we delete this, and we put in the optimized central part, switch to a single point calculation, and then we want to include all the cations here as an electric field, and that can also be done in the GUI. So let me show how that's done. Copy these guys here, copy, and then we go to model electric field, paste them here, and we put a charge of 1 for lithium and a charge of 3 for yttrium. And we need to change the occupations now a little bit, because these are just point charges. So we have less electrons. And again, of course, you can work this out on pen and paper. Just count how many electrons you have. So I'm just going to take this from a run that I've done before. And those are the occupations that we'll need. So we go to user input. So that's just a set of directives that will be added to your run file before you run your calculation. And then in properties, Ligand Field DFT, we need to set the occupations. And so let me see, we had 134, so that's 67 orbitals fully occupied. And that means in the Ligand Field DFT, we start from 68, 69, 70, 71, 72, 73, 74. Again, spin orbit set to 1. Main quantum number is 4, angular momentum 3. And now we can run the Ligand Field DFT calculation for F2 of praseodymium 3 plus inside the host material. So F2 LF-DFT inside host. Ignore the warning. And indeed, we need to switch to no sim, which it kindly has done for us. All right, so I sometimes forget that, but that's absolutely necessary for these average of configuration runs, as well, especially if you set the occupations. And just run this job. Let's see if that finishes within a reasonable amount of time. Now, since we don't have a naked cation anymore, we actually have it in a chemical environment. Note that the environment doesn't need to be symmetric, so it isn't doing ligand field theory according to the symmetry, but it's taking into account the chemical environment, which can be asymmetric. And that's going to take a little bit longer. So let me just show you some of the results. Let me see. So this is one particular result. So for this calculation, again, within this chemical environment, I'll show you the run file. It turns out that for the sorry, that's not the right calculation. That's it. And I'll show you, sorry about that, show you the run file. That for the F1D1 configuration, these are again the doubly occupied orbitals. These are the F orbitals, which we use to smear one electron. And then there are four orbitals, which are not occupied, and then followed by the D orbitals. So sometimes you need to run a single point calculation or try a number of different occupation options to actually occupy the d orbital. So that can be a bit of a challenge for the more interesting systems where you embed them in a chemical environment. So you can see these orbitals here. These are actually p orbitals, or a combination of p and s orbitals involving also the f electrons. So it can sometimes be a little bit difficult to get hold of the right orbitals. So that can be an interesting scientific challenge for you. Now let's pull up that spectrum. Also note, in this case, I didn't use a hybrid as has been used in the paper, but I've used the SWOT functional, SWOT 12 functional, which is designed to deal well with different spin states. So that could also be a good option for the lanthanides. I'll show the spectrum here. And again, we want to switch from ligand field energies to ligand field excitations. And here we have the spectrum. And let's see if we can compare it a little bit to this spectrum here. And so maybe adjust the scale a little bit and increase the Gaussian broadening a little bit. So you can see it's not an exact match. So at least the first peak at 50,000 centimeters is the same. And then there's another peak here, which is slightly shifted to the peak over there. And then there's another peak at around 70,000, which is corresponding to this peak here. So if you want to exactly reproduce this, we can provide the input files, and you can run them also with the Becker-Thurlip hybrid calculation. So this concludes the demo. I hope you understood the basics of setting up the Ligand Field DFT, as well as understanding a little bit the subtleties of setting it up for the actually interesting host materials for designing phosphorescence converted white LEDs. Let us know if you have any questions or problems.